Here we are going to explain about the CAN protocol. These are the contents that we cover in this section. Let's move to the introduction part. CAN is a multi-master serial protocol which was developed for automotive application. The main feature of CAN are robustness and reliability. Because of this, it can be used in many areas such as medical, electronics appliances, etc. It mainly deals with communication between various electronic devices like management systems, gear control, lighting control, etc. CAN frames. The CAN protocol employs four different types of frames to enable communication between nodes. Once the data to be transmitted is written to the appropriate mailbox, the CAN module takes over the control of data transmission and formats the data for transmission over the CAN bus. This is the figure which shows the data frame of CAN protocol. First, the SOF, which is the startup frame. The data frame begins with a dominant SOF bit. Next, STID, which is the 11-bit standard identifier which follows the SOF bit. SRR, this is the substitute remote request bit, occupies the same position as the RTR, that is the remote transmission request bit. IDE, identifier extension bit, which differentiates a standard frame from an extended frame. EXTID, the extended identifier. The 18-bit extended identifier follows the IDE bit. RTR, the remote transmission request bit, which differentiates a data frame from a remote frame. R1, R0, which are the reserved bits. Next, DLC, the 4 data length code which specifies the number of data bytes contained in the message. Next, data, which is of 0 to 8 bits. CRC, the 15-bit cyclic redundancy check, which holds a checksum sequence used to detect errors in transmission. AC key, this is the acknowledgement field. The last is the enter frame, which consists of 7 recessive bits. Next is the remote frame. The remote frame are sent by nodes that request data from another node. The structure of this is similar to that of data frame. The difference is the exception of RTR bit is recessive and data byte length is 0. Next, the error frame. The main feature of CAN protocol is that it provides error detection and correction mechanism. While transmission, if an error is detected, it immediately generates an error frame. The transmitter of the message aborts the transmission and attempts retransmission. The last frame is the overloaded frame, which is generated by a CAN node to delay the next message on the CAN bus. This is usually done if the node is busy with something else. The two fields of overload frame is overload flag and overload delimiter. Now let's move on to the layout of CAN protocol. The table shows the layout of all mailboxes in the 24x bar 240XE. It occupies 8 16-bit locations in the mailbox RAM. The address offset starts from 0 and ends with 7. In MSG IDNL, if an extended identifier is used, then the lower part of the extended identifier is stored in this register. A standard identifier does not use this register. Next, in MSG IDN4, if an extended identifier is used, then the upper 13 bits of the extended identifier is started in this register. If a standard identifier is used, the 11-bit identifier is stored. In MSG LTRN register, it has the data length code bits. This bit specifies number of bytes to be transmitted in a message. Last, in MBOXN, We have MBOXN A, MBOXN B, MBOXN C, and MBOXN D. Commonly, we call it as MBOXN X register, which can hold 2 bytes, giving a total of 8 bytes storage space for each mailbox. The next topic is CAN module initialization. The CAN module must be initialized before it can transmit or receive message packets over the CAN bus. This is done by writing the appropriate values to the values configuration and control register. The initialization task can be broadly divided into 3 steps. Step 1. Assigning the MSGIDs. The assignment of unique message IDs to the various mailboxes makes a CAN module capable of filtering messages, thereby accepting only those messages intended for it. All messages that are used should be assigned unique message IDs. The MSGID of the transmitting mailbox is always attached to the transmitted message. Step 2. Enabling acceptance filtering. If acceptance filtering is used, then the decision whether to accept a particular message is taken based on 3 parameters. They are MSGID of the incoming message, MSGID of the received mailbox, configuration of the local acceptance mask corresponding to that received mailbox. Step 3. Configuring the bit timing parameters. The bit timing configuration of a CAN module must match that of other nodes on the network. The bit configuration registers are used for this purpose. The last topic is CAN protocol signals. Basically, a CAN bus have 2 logical states, dominant and recessive. When a logic low level is applied to transmit input pin of transmitter, the dominant state occurs. And whenever a logic high level is applied, a recessive state occurs. If VDIF value is less than 0.5 volt, then it is recessive state. And if it is greater than 0.9 volt, then it is in dominant state. If VDIF value is between 0.5 volt and 0.9 volt, then best state is undefined. Since the difference between the two signals is used to define the state of the bus, this is known as differential signaling. Since CAN H and CAN L are used to determine the logical state of the bus, they are referred to the complementary signals. We can find the value of VDIF by using the following equation. That is, VDIF is equal to V CAN H minus V CAN L. Thank you.